Alrighty. Hello everyone, my name's Kit, and today I will be going over the Advent of Coding 2021 Day 19 Programming Challenge. So this is the one with the scanners. So let me just open up the notes that I took for this first. Alright, so for this specific problem, we have a bunch of scanners, which we can just think about as like cubes currently floating in space. And for these cubes, these scanners are used to scan like some different beacons, which can be in various different points in space. And we have a bunch of scanners that are placed around this like 3D dimension. And the problem is that they can be in various different orientations. So for the first problem, what we're trying to do is just find the unique number of beacons. So first, let me just walk through like how I think about the scanner orientation stuff. So for the scanners, we have 24 unique orientations. And the way that you can kind of think about it is that for each of these boxes, if you think about the scanners in terms of boxes, there are 6 sides or faces that they can be facing. And then for each of these different faces, there can be 4 different rotations. So this is an example of how the 4 rotations could look like. So if it was facing this way, then we could have a 90-degree turn counterclockwise like this, 90-degree turn like this, and then etc. etc. So since there are 6 sides, and for each side there can be 4 rotations, in total there are 24 unique rotations. Okay, so when I talk about these scanners, here's the coordinate system that we'll be thinking about in terms of like this face. So if you see a face like this, this will be the x-axis, this will be the y-axis pointing up from the box. The z-axis is like pointing opposite of the face, so like pointing that way, if that makes sense. So if we think about these scanners in just 2 dimensions for now, this is like an example of what they could look like in space. Right, so we have one scanner here, and this scanner scans these points. So this is 3, 4. So this point in relation to this scanner, it sees it as being at position 3, 4, which is the x position, then the y position. This is at 5, 2. And then if there was another scanner that's close by, which is also like scanning the same beacons or the same points, in terms of this scanner, the coordinates of these points would be like this: 1 and -7, because here the x-axis, so the first number here is the x, the second is the y, so this corresponds to like this x here, so it goes up 1 and then down 7 times, so 1, 2, 3, 4, 5, 6, 7. So this is from this point right here. This is the 0, 0 for the scanner 2. Then same goes with this point here. This other point in terms of the S2 coordinates is 3 and -5. And then this scanner could be scanning some kind of point that is unavailable for S1, like it might be too far away. So for example, there's this 2, 3 point here. But as you can see, if we translate it to S1 coordinates, it will be 13, 3. Because we just count like the number of spaces. So like if you count here, this is 13 and then it goes up 3. So this is 13, 3 in relation to this S1 coordinate system. Okay, so for the first problem, the algorithm that I decided to go for in order to solve this was 1. first we find the scanner translations. So the rotations and flips necessary to get the S2 cube in the same orientation and position as the S1 cube, or the S1 scanner. Then 2, we translate all the points to a single scanner coordinate system. And from that, we can basically find all of the unique points, and that is really easy to do. We just use a set, and then we store all of the points that we translated into a single coordinate system into that set, and all of the points there will be all the unique points because they are all translated into just one coordinate system. Right, so here's an example of number 1. How would we find the scanner translations? So for example, this one, if you were to do it manually, so first we had the scanner, which was in this orientation. It's pretty obvious that we need to rotate it 90 degrees around the z-axis. And once we rotate it around 90 degrees around the z-axis, we get this orientation here, or this rotation. Then afterwards, all we need to do is calculate the offset. So how much we need to move the scanner by in order for it to be like in the exact same position as this one here. And it turns out that this is -10 and -5 for this. So if we move this scanner -10 coordinates or units to the left, then 5 units down, then it will be in the exact same position as scanner 1. Okay, and then afterwards we just translate all of the points for this scanner in terms of scanner 1 here. So here's an example of how you would do this. So you just do like -7 minus the offset. So this is 3. -1 minus the offset, which is 4. And you see here that we get 3, 4. And same goes with the 5, 2 here. Okay, so the important thing to note here, and a clue that the problem gives us, is that 12 points overlap for some of these scanners. So by using this fact, we can get these the rotations and offsets necessary to get some of these scanners in terms of another scanner. Okay, so yeah, that is basically the main crux of the algorithm. Now I'll just walk through the code as to how I actually did it. Okay, so here's my vector3 class. It annotates, or it has functions for rotating around different axes. If you want a breakdown of how to think about this in the 3D world, I also created a video about that. I'll link it below if you're interested in knowing how to think about that. But yeah, so a vector 3D is just a data class with 3 variables representing the x, y, and z. And then if we go down here at this part 1, so this first piece of code here is just getting the scanner data for all of the different various scanners and just storing it in some kind of wrapper class. I named it scanner data. So if you see here, scanner data, I gave each one a unique ID just to make it easier to reason about. And then each one holds a set of points in their own coordinate system. Then the way that I did it was that I decided to store all the unique orientations for it in a list here. So this list would have like 24 different lists, and this orientation config contains the orientations that we need to get in to that specific orientation. So the indexes of this and this corresponds to one another. And if you look at orientation config, it's just telling you the number of x rotation, y, z rotations, and the x and y flips in order to get the scanner into those different orientations. Okay, so that was this was pretty straightforward to do. I just decided to do it the very janky way. I went through all the possible X, Y, Z, X flips, and Y flip, um, like available rotations and flips that we can do. Then I just created a set of these different orientations and stored it into a list here, and also the configuration for getting that specific orientation. Yeah, I stored the configuration to get to that specific orientation. Okay. Okay, so next the next thing I did was I just scanned through each scanner, so just like a cross between the first and then the second, and then I had this overlapping method which I used in order to calculate like all the translations and orientations needed to get from one scanner state to another. So like basically step number 1 here. And the way that I did it was that I went through all of the unique orientations and just basically looked for one where like the offsets for the X, Y, and Z, that there were like 12 points that had the same offsets. And if there were 12 points that had the same offsets for the X, Y, and Z, then I know that it's one of those overlapping scanners with 12 points overlapping each other. So by using this, I was able to get the offsets for in terms of one of these scanners. So the destination is this. So basically how to get from this scanner, this other scanner, to the scanner that currently stores this data. Okay, so after I get all these overlapping results, next was getting the translation configs. And for this, there were actually this whole block here. So from getting that from the overlapping results, I already know like how to translate between some of the scanners, but not all of them. To get all of them, what I did was had a while loop that just kept repeatedly seeing if there were any scanners which I can convert into another scanner. So like for example, let me just show you here. So if I knew the translation from 1 to 2, and I had the translation from 2 to 3, then to translate from 1 to 3 is basically to do this this translation. So T1, then T2. So I just scanned through all these orientations and found like these different sequences where it was matching for like the destination and source, and then that was how I was able to get 1 to 3, T1, T2. So I did this for all the scanners until there weren't any available translations left. Right, so in the end, we would have these various translation configs, and once we have all these translations, all we need to do now is convert all of these scanners into just one single scanner coordinate system. So this is what I did here. So I iterated through all the scanners. I translated the points for each scanner in terms of the scanner 0 coordinate system. Then I built a set. So then I got all of the unique points, beacon points. Then I just printed out the size, which would be the the answer for part 1. Then for part 2, it was pretty simple since we already know the various like offsets and translations needed to get into different scanner coordinates. You just iterate through the cross between scanners and all other scanners, and then calculate the largest Manhattan distance. Alright, so here, for example, we already know that this is at 10.5. So yeah, we could just calculate the Manhattan distance for this after doing the translation, because we already know the offset. Cool, and that was basically it. So yeah, let me just go ahead and run this and show you like an example of how it looks like here. So currently it's running, checking all of the orientations to find some of the X, Y, Z diffs and check if there are more than 12 overlapping points for each of these diffs. And if there are, then that is an orientation config that works. So here you can see I printed out all the different translations. So via that while loop, this is like from how to go from scanner 31 to 0, scanner 31 to 1. These are all the various configurations that you would need to translate between each one. And for each of the 34 scanners, or 36 scanners, it should contain everything, all the translations needed. Cool, and then afterwards, I printed out all the beacon points, but that's really unnecessary. It tells me there are 445 unique beacon points after converting to scanner 0. Then the Manhattan distance was just iterating through all the scanners. Since we already know how to translate to scanner 0 coordinates, we did that, and then we found the distance between each of the scanners in terms of scanner 0. And yeah, that was basically this problem. I'm sorry if like it doesn't make that much sense. Hopefully, like looking at the code will be clearer than how I explain it. It is quite difficult for me to explain, since this code is actually quite a lot. But hopefully this helps. Thanks for watching, and bye.